I recommend this whole video. Dude, talk about that.
API.
Yep. Okay.
The sender and receiver both define the post-quantum HPKE.
After this goes, I'm bias here. I'm co-author of X-Wing. Very proud to see this get shipped to all these users. It's a good crypto scheme, in my opinion. Now look at the source code. It's all formally verified. We don't know much about how they did that. It's all C code that ends up in the secure Enclave and then CryptoKit and all that. This is also shipping too, which is pretty great. So in iOS 26, iPadOS 26, macOS, Tahoe 26. Hey, can I, is that available yet? Mine tools, yes. So maybe.
Patient less.
Automatically advertise for support for hybrid. So this is not X-Wing, this is the TLS specific X25519 ML-KEM 768 hybrid key establishment. They didn't have to use X-Wing because of the way that TLS 1.3 is. Just makes it easier to do things that you had to do. It's doing it already. Thinking which is the spec for X-Wing. Because of reasons, it is an independent internet draft. That's the important part. So take your ML-KEM bit, X25519, you do this. Once you have your public key, or your key pair, bust out all the pieces of your key. You do an ephemeral elliptic curve key pair. You send your long-term key. Well, not you compute the kind of Diffie-Hellman with You do a Diffie-Hellman and you send out. Well, you generate the public key side of your ephemeral key. That's the quote ciphertext, the ephemeral key for this encapsulation round trip. And then you do the Diffie-Hellman with your long-term public key and get a shared secret. You do ML-KEM Encaps against the public key. You get the ML-KEM shared secret and the ciphertext for ML-KEM. And then you combine the ML-KEM shared secret, the X25519 shared secret, the Diffie-Hellman value that you computed, and you also include the X25519 ciphertext as the ephemeral public key that you just generated for this, and the X25519 public key that you're encapsulating against, or you were doing the Diffie-Hellman against that someone sent you. All that together with your combiner, which is literally the hash function SHA-256 down here. SHA-256, but with a label. And that label is literally this funny little art. It's supposed to be a X-Wing starfighter, superiority fighter from Star Wars. We're all nerds. We're all nerds here. And then you do the same thing on the other side. You decapsulate, you do a curved Diffie-Hellman, get shared secret and a shared secret, and you take all that public data again, and you shove it in there, and you 56 it with the label at the end, and that's your shared secret. One very good thing that led me to look at some other stuff is in X-Wing, the private key, the secret key for a hybrid KEM key pair is a 32-byte seed. You use that 32-byte seed to generate the entire key pair. You take your 32, put it through this extendable output function, shake256, take those 32, and you say, shake256, give me 96, that's 96 times 8 because they parameterize it using bits, but give me 96 bytes. It says, sure, I am a sponge function. I'm with these specific finite values. I'm indifferentiable from a random oracle. I'm very good at this. So we get 96 bytes, and of those 96 bytes, we take 64 of them and split them in 32 bytes over here, 32 bytes over here, it's 64 bytes, and we hand it to this FIPS compatible interface for ML-KEM 768 to generate the ML-KEM part, and we take the rest of those bytes, 32 bytes, to generate our X25519 secret key. It's a scalar, and then we use that doing some elliptic curve math, get the equivalent public key, and then that's our expanded key, but the secret key, the encapsulation key, is that 32 bytes. So you go down here, you encapsulate against this whole expanded, this is the Diffie-Hellman part, and this is the rest. This is the full ML-KEM part. But when you're decapsulating, look at that. is 32 bytes because you have to expand it. Expanding it takes 32 bytes. I see somebody in the chat, but my chat window is not showing you, and I'm very sad. I don't know why that is. Oh, how about... Let me try that. Doesn't do anything, but... See you over there. So, that's what counts. So, one, the seed stuff is very nice and very exciting because one, we love a 32-byte seed. We love a small key size from which we can generate all our other key material. It's deterministic. You have a single value. It prevents you, like someone trying to like swap in one ML-KEM key pair with another elliptic curve Diffie-Hellman thing. It's very good for like detecting manipulations, either manipulations by someone on purpose or by some fuck up. But also it gives us nice like cryptographic properties that basically means all of this stuff is really tightly bound together. So when you are doing these decapsulations and encapsulations, it's like the shared secret that you get out here and here, like it's practically impossible for that shared secret to be calculated for a different key pair, even if they try to manipulate the key material. Because if they tried to manipulate the key material in some way, even if they had access to the secret key material, it would be detected and it would give you a different output. So when you use the shared secret that comes out of X-Wing, it's like tightly bound to the keys that are used and the ciphertext that is generated by those keys. So that when you're using this in your protocols, which the Apple stuff shows, it gives you really strong guarantees that can be hard to do if you combine things in a different way. The X-Wing, so exciting! And yeah, I want to look at their API here. So I want to download the kit. Where is it? You just reset this other landing page. Common people, is that one I'm thinking I can download, but I can't? Alright. I really want to look at that. This is Swift Crypto. Like, they literally just landed some of this stuff, like, in the past couple of days. Alright, in the past month. Yeah. Speaking of swing. Hey. Oh, thank you. Thank you, Strad. Hi, Strad. A few months ago. Yeah, okay. Alright. No, that's 5 months ago. 2 months ago. Yeah. Like, these commits are so funny. Like, okay. I'm very perfect. It's somewhere.
Restricts.
Yeah. I'm just gonna discard. Yeah, the ASCII art, that was a cute idea to get some good domain separation, and we twiddled it. Actually, that specific ASCII art is that way to fit exactly within the rounds of Ketrek for SHA-256, so they would not overflow the capacity, I think, to make sure it would all fit in, the whole input would fit in like one, however, like a nice even number, it would not overflow the round size. So that got twiddled a little bit over time, and it may be influencing other IETF hybrid crypto schemes because everyone wants to keep X-Wing, and X-Wing has a funny little ASCII art domain separator label. So the X-Wing would be the outlier if we gave I had like a bunch of really boring domain separator labels, like this is the style, these are the components, this is the function you use, this is what you use to expand the seed, and like it was very clear but long and boring. And now it's like, well, we really want to keep X-Wing, and these other things, they could have ASCII art too, so we might try it. Yeah, we'll see. This is definitely one of those bike sheds of writing specs and writing and naming things and things like that will probably never quite finish, or at least it'll take a while. But it's changed several times already, and it'll change again. Who is that emoji, Strad? Looks funny, but okay. Changes to their KDF. They are still extract and expand, which is funny because they're implementing X-Wing, and technically SHA-3 is it's being used as a KDF, and it's a one-shot. And for other fun stuff, there's a new HPKE working group in the IETF. HPKE publication kept efficient. And where is it? I think this was like an idea. I was like, hey, we're using SHA-3 as a KDF over here. Oh, I don't think it's been adopted yet. But it's a one-shot. And the HPKE, you wanted to use SHA-3 as a KDF in HPKE, it doesn't fit because as currently written, HPKE specifically defines a KDF to be the extract and expand paradigm, just like HKDF is. Not hash literally everything, including C1 and C2. Aha, so yes it is. For X-Wing, the reason we don't literally hash everything is because specifically picking ML-KEM has these nice pre-image security properties about it, partly because of it itself using SHA-3 inside of it, but there's more to it than that. I'm pretty sure there's more to it than that let us prove that we can get an NCCA hybrid KEM using just the shared secret that comes out of ML-KEM inside of it because of this pre-image resistant property, the ciphertext pre-image resistance property that's called a ciphertext second pre-image resistance. And this is a property of ML-KEM. There are other KEMs can also achieve this. I think we originated this kind of specific fine-grained notion in the X-Wing paper. And I'll pull that up actually. And no, this is the problem with naming your thing after a popular IP name, is that you are thinking in cryptography. Everyone else is thinking in Star Wars, so you have to be more specific. So this is X-Wing paper with our proofs of security for the whole hybrid KEM. And the main property that everyone wants from a secure KEM of any kind, hybrid or not, is INCCA, which is indistinguishability under chosen ciphertext attack. You're saying the ML-KEM output is already SHA-3 hash of everything it saw. Yes-ish. Indirectly, let me go into my good friend, ML-KEM FIPS 203. I'll bring up what we got for... I keep doing this. My mic is mono, my music is stereo. Let's see, I'll fix this. I keep doing this in OBS, and I could fix this. Testing. All right, I think that looks correct. The annoying thing about this is there's a tick in the properties in OBS. And literally, if you have a mic that does this, or whatever, a mic to interface to whatever pipeline, there's a thing in the thing, and it says mono, and it's default unticked. To actually get the same channel in both sides, left and right, you have to tick the mono box, because my channel is mono, but I want to output it in stereo, the single channel on both channels, so... I always get confused about that because UX runs everything around me. Okay, so popping the stack, how many layers of specter are you currently last? So, all right, so let's look inside ML-KEM. These are internal and dekernal because you hand the randomness to them. So decaps tends to be the most important. So what you do when you're generating your shared secret in ML-KEM that we use in X-Wing, you get handed a ciphertext from your possible adversary, and you have a decapsulation key, your secret key. You do all the parsing of the ciphertexts and the decapsulation key and all this sort of stuff. So this H value is actually the hash of the public encapsulation key, and you theoretically calculate that hash when you're computing and serializing your material, but it could be manipulable by an adversary. And the Z here comes into play only if something goes wrong with the decryption, the decapsulation. So we hand our ciphertext to the underlying public key encryption scheme, and we decrypt it with the part of our secret key that is the decryption key for public key. So, and we get this M prime, which is our possible random message, random nonce that we have generated and encrypted to share with our adversary, with our party. You take this random value, you concat it with the hash of the public key, of the whole encaps key, and you put that through, I'm pretty sure this is SHA-3 256. Sorry, SHA-3 512. Right? I might be remembering it wrong, but yeah. Oh, it's 2, that's why. It's not, if it was just K, That's what it is, because J is another 256 value. It's actually she. The reason these functions are all different, H, J, and G, is they are length and kind of type domain separated. They're all instead of having a label for each one of them, that's domain separated. So it outputs, I'm pretty sure that's 32 bytes for that R prime and 32 bytes for the possible shared secret that we've computed. So this is committing to the random value that the possible adversary encrypted to us. Whoever sent it should be the trusted party, and the hash of the encapsulation key that theoretically did the encapsulation to us and the encryption to us. And then we recompute, this is the FO transform. This is a little bit expensive, but we recompute the ciphertext given the encapsulation key that we already have, that's from the key material, the randomness that got sent to us, we're going to try and re-encrypt it to ourselves, and the randomness that got extracted from, this is part of making the random public key encryption scheme deterministic. You need it to be deterministic, and the way you make it is you literally like pre-compute, you have a deterministic way of computing the randomness, and you hand that randomness to your scheme. You get your ciphertext back out. If the ciphertext that you yourself compute with all those values matches the ciphertext that possible adversary handed to you, then everything's hunky-dory, and you hand back K prime, the shared secret, and you hand that back. If they don't match, you compute this other thing based on this value that's part of your secret key and the ciphertext that the adversary handed you, and you give out this other value, which is called the rejection value, the FO rejection value, so that you have something that's pseudo-random and cryptographically random, but it's like pulling the escape hatch value. This is controlled by the adversary and controlled by this other randomness. If there was a nice cryptographic way to throw an error in a way that wouldn't result in someone throwing away an error and just using all zeros as their secret key to encrypt traffic with, they would do that, but we don't. So this design used to include the whole ciphertext in it as well. When you hand the ciphertext, it would use like hash in the ciphertext and include the hash, and that it was including in the hash of the public key, and it was using there in a nested sort of nesting dolls of hashes of all this key material. It was found that you didn't need to include the ciphertext for some reason. I don't remember what it was, but it made the proof of NCCA for ML-KEM nicer and tighter and have the security bounds of picking the parameters and like how much tolerance there was between ideal and instantiating and all this sort of stuff. It made that better. And this ciphertext can be large. So for the largest parameter set, the ciphertext is 1.5 kilobytes. So if you don't have to hash all of that in, you even with something as fast as SHA-3 and Shake, that's nice. And they didn't, so they were able to do that. But that is not exactly why. It is obtuse ways to get the hash domain separation, but like when you have FIPS 202 that gives you this kind of suite of pretty nice, all kind of family related functions, you've got your SHA-3, you've got your Shake, and you've got all these different sizes. You've got 5 different sized things all in one FIPS happy family. I think one of the first versions of Kyber, which became ML-KEM, used Shake everywhere. It might have been Shake 256 everywhere, and they did like explicitly domain separate, but I forget. They changed it several times on the way. Yeah, it's definitely a way to ensure impulse provide all of them. Yes, it is. So all of this is not exactly why we don't include the ML-KEM encapsulation key and the ML-KEM ciphertext in the preimage in the computation for X-Wing. It's because we're able to prove that ML-KEM provides this second pre-image resistance thing. And let's see if I can sum that up more closely. I've talked elsewhere of these binding properties. In the earlier version of this paper, let's see, can I have versions? Do I have all versions? Yeah, let's do that one and the latest one. This is the first one. Let's see. In an earlier version, yeah, this property was called ciphertext collision resistance. There's this whole suite of security properties that are being analyzed for KEMs called binding properties. And those are mostly collision resistance properties of like, if you are spitting out a shared secret out of the back of a KEM, what does that tell you about the collision resistance of inputs like ciphertext into computing that shared secret, inputs like public key material? What does that say? Or like if you have a key and a public key, does that bind to a possible ciphertext as an input? How you compute those? And by bind, is there a possible collision in the set of possible values? And it's said to be strongly binding if that collision is basically impossible. But this was the first version of X-Wing, and then it eventually got turned into the version that was final, which is instead of that collision resistance, it's pre-image resistance, and it's specifically second pre-image resistance. MPC stuff, maybe. There's definitely like interesting MPC in the head stuff that I like in the post-quantum signatures on-ramp for NIST. There's a ton of MPC in the head constructions, and it's literally just like taking a whole MPC protocol with sort of message passing between parties, and you compute blah, 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 and you have finally something at the end, and you like hash it all, or you put it all through a block cipher construction or something like that, and you just like smush it all down, and you can create like the way that you might have like a signature protocol or a fiat, something that's like a protocol that's like multiple parties talking back and forth, and you can apply like a fiat chain or transfer to them. You can do something similar like that to MPC stuff, and you can make a signature out of it. I might do that in the future because there's a ton of those. I also am into like threshold protocols, which is like a form of MPC. I worked on Frost, which is a threshold Schnorr protocol, pre-image. Second pre-image resistance. We show that ML-KEM provides ciphertext second pre-image resistance. Design the efficient KEM. And let's go find the rest of it. Yeah, there's actually a nice paper that just came out. Chelsea Comlow, like co-designer, like originator of Frost, the original protocol. I helped a lot, like turning it into a specification in IETF. She was the original author with her advisor, Ian Goldberg. And Mary Maller and Elizabeth Kreitz, and I don't know if there's anyone else, where they basically showed there was an interesting result about adaptive security in protocols like Frost. And it basically said some things that we thought were doable might not be doable. I want to go read that, and that might be a very good way to like go back in time and revisit Frost for me. I have like a stack of papers that just keeps growing, like a metaphorical stack, it's whatever, of things I just want to read on stream and like whatever. There's like that paper, there's a security proof for the new security proof for the update version of SkiSign. There's like a teardown of, I think it's WhatsApp encryption or something like that. It's all over the map. Boo, whatever. Okay, so second pre-image resistance is basically once you decrypt, decapsulate your ciphertext based on the thing and it equals K, can we make sure that this is never going to have a different ciphertext that would allow you to compute this, basically? So if you see here, we can compute and we do an encryption to another C star. Now, if we give the adversary our whole looking material and the shared secret that we give out and the ciphertext, can the adversary guess which one of these is the correct one? Which is basically what, like, can you do a guessing game and detect which one of these is the right ciphertext? Which is basically able to guess, like, which of these you put in to get the key that you want. Yes, so the adversary gets access to the secret key, the encapsulation key. This allows us to have it hold even if all the other properties are done. And I'm going to make sure this doesn't get too warm on the screen. Even if all the other security notions, such as NCCA. So this is an independent notion of the NCCA. This is independent of the NCCA game. It's actually nice because I'm pretty sure all the binding properties that are collision properties rely on NCCA to hold. I forget, but it's like it's operating in a world where NCCA is like a capability and you're supposed to be resistant against an adversary that can do that sort of trickery. Yeah, this allows us to prove the security of what we used to do to construct X-Wing. So it's the strength of the nominal group of an arbitrarily bad KEM. Nominal group, this is actually pretty great because this actually means that if there's a bug in ML-KEM, in an implementation of ML-KEM that would like harm or reduce the NCCA-ness of the like implementation of ML-KEM you're using, which we have seen for reference implementations of KEMs in the NIST competition, where like on paper, if you do everything is correct and we have a proof of but the implementation had a bug. The implementation did not match the thing that got written down and had a security proof written down. It had a bug. And so the NCCA-ness did not hold in practice. What this is saying is if something happened into an implementation of ML-KEM, that the whole construction of X-Wing it remains independent of that. So it's a nice little like benefit of like making your security defined this way. But it is like, this is extra work that a researcher kind of has to do beyond just saying like, here's a KEM, it is NCCA, that's what you need, right? Like if you have an NCCA KEM, yes, you can just make a whole bunch of assumptions about it, but it does usually mean you need to include the shared secret and the ciphertext, and hopefully also your public key when you're doing stuff with it, whether you're just using it on its own and you're putting it into like a key derivation tree for a whole protocol like TLS or whatever, or SSH, or you're doing something hybrid with it. You do have to put the ciphertext in, and you probably really would like to put the public encapsulation key in for just a regular schmegular and NCCA KEM. But for this is extra analysis that doesn't rely on the NCCA-ness, but lets you get away with being more efficient and excluding more stuff. Right, okay. So ciphertext second pre-image resistance is related to the key binding properties and the keeping up with the KEMs. Instead of finding any collision, like the binding properties, we opted for second pre-image resistance notion as this fits the requirements for the proof. This is a strictly weaker notion. So when we say strictly weaker, we mean you have to take less on faith if we have to hope that this is true less for this notion, as opposed to like this is a strong notion, as in like we're making a lot of assumptions here and we're biting off a lot, whereas this is weaker. It means like we're not biting that much off. So that's nice because we're not asking us to take a lot on trust of this notion. The adversary is tasked to find a second pre-image instead of any collision with the ciphertext. This allows us to prove there are concrete bounds in the chief security level. I won't go through the whole proof since this is a multi-game hopping proof, and I've looked at it a couple of times and I've still not gone through it bit by bit. Yeah, exactly. Yeah, strong as an alcohol content, not strong as in tensile strength. That's good, yeah. Let's see if I can get to the end of the game hopping and so you can give an intuition. Because I did not write this proof. My co-authors wrote this proof. I think there's also a proof in the Q-ROM. This is in the ROM. Actually, I forget which side of it is. I forget if this is which side. There's two proofs. Yes, this one's in the ROM, and I think on the other side, it proves something in the standard model, and I forget what it is. I think it proves in CCA in the standard model or something like that. I don't know if that makes sense. I think you might need a random oracle, I forget. But two random oracles. Yeah, reduction to the security of the KEM in the standard model. So this is the other side, which is you can have an NCCA KEM, one adversary, two adversary, three adversary, and then we've got the PRR. But that's a different argument. Replace the shared challenge key with the uniform random key. With this change, we've reached NCCA game instantiated with QSF. Chosen uniformly at random, which means G4 matches the definition of NCCA over QSF in the adversary game. So we call our nominal proof a random oracle adversary, making it most QH queries to the random oracle. And C, and this which queries its own DH oracle. Secret keys from the next theme. Choose the secret keys instead of opponents instead of honest families. Use the CH problem. Strong. That's statistical. Found the probability. This is forcing me to go further into the proof. Game when A would query HPKE. This is all about using ML-KEM as second ciphertext pre-image resistant to prove NCTA, but not explaining the way I would like. In 2, game 3, introduce the changes and the answer from cream into encryption oracle encapsulation. Ciphertext C1 is different from ciphertext C1 star. is used to generate the challenge ciphertext D star. The result in the same K1 as the K1 star is used to generate K star. So, granted. So the adversary says adversary A's B wins if the adversary A would trigger the abort. It's up here. So that's abort 1. There's abort 2. Okay. Yeah. So it's basically saying we're able to prove it inside out, I think. Or not equal. You want it to I'm going to try and get through this.
I'm neutral.
Okay. Bob. Yes. All oracles are simulated perfectly. Anything possible since C also includes the secret key finished challenger. C stops back on board 2 would be hit in G3. When the stop instructions reach C, obtain a K1 that's equal to K1 star, but like C1 and C1 star are different. This means C found a second ciphertext that encapsulate to the same shared key as the challenge key K1 star. Check C1 is therefore a correct answer for the C2 PRR game. So on our next hop, we replace the shared challenge key to start a uniform random key with this change we reached in CCA1 in CCA game differentiated for that. So is that in CCA? Oh, that's not a footnote. Okay, in CCA 1 as opposed to just before probability game 3 adversary 1 outputting 1. View of the probability game 4 adversary outputting 1. Okay, to prove this change I'm technical gray. There's OP is independent of the value of K star. 3. The random oracle is independent. K C1 or C2 must be different. K1 star, C2 star. C1 is different, and the resulting K1 being K1 must be different than K1 star, otherwise the abort condition will be triggered. If C2 is different, the input to the random oracle must also be different since it's including its input. So the behavior with the caps oracle is independent of the value of K star. Since the behavior of all oracles is independent of K star, the adversary cannot detect this game hop. Good. That means if the K star is choosing to formulate random, which means that the G4 final game matches the definition of the NCCA 1 QSF a game perfectly. Therefore, the probability of game 4 against the adversary outputting 1 is equal to the probability of NCCA QSF against the adversary outputting 1. Okay, that's that proof. Oh, this is probably what I wanted. Sorry, LMSC 5K Plonk. Okay, it's important to show that ML-KEM is C2PRI second ciphertext pre-image secure. Okay. With all these values, these are values that are specific to ML-KEM as defined in the FIPS spec. Integers greater than or equal to 1. This is the PK encryption and PK decryption, not to be confused with ML-KEM encapsulation and ML-KEM decapsulation, which is why I put caps and encaps as opposed to encrypt, decrypt, but that's just me. But G and J, the independent random oracles with output sizes of 5, 12, and 256 bits, they be an adversary against the C2PRR security, making at most Q sub G and Q sub J many hash queries to the random oracles G and J. Then the advantage is blah, 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 less than or equal to the number of queries to that random oracle plus the random oracle queries to the other random oracle plus 2 to the 256 because we output 2 to the 256, 256-bit secrets. And pretty sure. Okay, so we saw this earlier. It's very similar from what we have written down in FIPS. Oh, we have how many hops? Not that many hops. All right, let's go do this. All right, so the shared key K star of the challenge, of the game up there. Okay. K star of the challenge with the adversary is trying to find a second pre-image is generated by the random oracle G. That's true. We have this, since this key was honestly generated using ML-KEM encapsulation. So we have 3 cases to analyze. The first is the adversary finds a second ciphertext C that is different from the challenge ciphertext C star, but results, so that's the second pre-image to all of this, but results in the same input to G. So we're looking for another pre-image, another ciphertext that going through here. So this is different than colliding. This is finding another one that's like results in the exact same thing. You're giving a separate input that will go through here and result in the same input to this random oracle, a second pre-image to this random oracle. This has to go through, this is reliant on the properties of the public key encryption, and this hash is the hash of the encapsulation key that was encoded into the whole decapsulation key. Those are the same input to G. In the second case, we need to analyze the probability that G will output the same shared secret with a different input. This is relying on the niceness of SHA-3 as a good and pre-image resistant function. The last case we need to analyze probably the J, this other guy, for the FO rejection computation. We'll up with the same shared secret as the last one from the challenge. Okay. Input to G collide. Suppose PKE decryption outputs the same M prime for two different ciphertexts. That would be bad. That has happened in other KEMs. Intermediate values K and R prime are the same for both decapsulations. Since public key encryption is deterministic because we hand it the randomness, make it deterministic, C prime is the same for both decapsulations. This also means the equality check cannot succeed for both ciphertexts over here, right? This leads to a contradiction, so it can't succeed in this case, since at least one of the ciphertexts has to be rejected, and therefore the key generated by J is returned. Okay, so one of these, has to be wrong, and some other case has to happen. Okay, the output of G collides. The output of G is interpreted as the two values K and R prime. Adversary can already find a second pre-image of the decapsulation function if it can find a second input to G that results in the same output K. Since G is modeled as a random oracle, therefore behaves like a random function, the best the adversary can do is query the random oracle, hope to find input by chance. And we have nice proofs of SHA-3 as indifferentiable by random oracle, so this is actually solid. Therefore, the probability, and we have proofs for other stuff, not just SHA-3 and Shake. Therefore, the probability of an adversary finding such an input is bounded by the number of queries QG plus 1. I forget what that is. I think it's the one we do every time anyways, right? Over 2 to the 256, where the 1 over the 256 comes from the possibility that the adversary does not query the random oracle on this value, but a collision-causing query is performed during the decryption done by the game. Yeah, okay. And then the last case, the output for the FO rejection value computation, output of J collides. Input. Since J is a random oracle independent of G, best adversary can do is query the random oracle J to find such an input by chance. Yep, QJ plus 1 over 256 for the same sort of reason. Okay. I'm not that good at proofs, so sure, looks like it. Anyway, we have a proof that ML-KEM is ciphertext second preimage resistant. That's why for X-Wing, we only include the shared secret that comes out of ML-KEM, the shared secret that comes out from computing these Diffie-Hellmans, the ephemeral public key of this round, this encapsulation's ephemeral public key Diffie-Hellman. That's this guy. Encapsulation, where is it? C2? Here it is. This guy. And your long, quote, the long-term public key, the part of your full hybrid public key, the Diffie-Hellman part of that, we include that too. Because we don't have these properties about this version of DH-KEM, but without the full KEM part. If you treat all the ML-KEM parts as just extra gobbledygook that has no security properties, the whole thing kind of devolves to an instantiation of DH-KEM, so you still get a NCCA secure KEM with okay binding properties, depending on how do we do this? I think we put the whole thing in. And there's like proofs about including the whole serialization of the public key points, the X and Ys, and blah, blah, blah. I think for X25519, we're fine. I think we get a pretty good malbind-ish thing if this devolves, but either way. But because we have these proofs of these properties of ML-KEM, the way it's constructed, we leave out the ciphertext and the encapsulation key because we can prove that we get in CCA, even ignoring all that other stuff. But yeah, where's the other side? There's the proof on the other side. We did our proof of NCCA in the ROM. Yeah, reduction to that in the ROM. Where's the standard model? Yeah, reduction to KEM in the standard model. So this is reducing. Where are you? Back where you were before. Yes? Where was I before? Now the bottom? This? Is it this one? Is it this? So in the spec, this got flipped around, but literally this is a label, a domain separator, to make this whole instantiation of this hash function. The technical formalism of what this is doing cryptographically is oracle cloning, as in random oracle cloning. And there's a lot of simple ways to do this inside ML-KEM. They use different lengths The different outputs have different lengths, and so those are different random oracles. But in this case, SHA-3 is domain separated from all the other instances of SHA-3 with a label. Literally like a label in here so that all the queries to it, including all this bag of bytes here, are separated from other queries, other inputs to it with a similar length, and allows you to model these cryptographically as separate random oracles. So if you see cryptographic schemes, I'll show you one. We were talking about Frost. It uses a single like hash function or a similar function, and they like use it for a bunch of different things. Use one function, and then you domain separate it into like we have 5 different functions. I like the Ristretto one the best. So for this cipher suite of Frost, we use SHA-512, not SHA-3, but SHA-212. And then we instantiate 5 different hash functions by computing SHA-512, some extra information, this domain separator row, which is the equivalent of those little squiggly lines, and then whatever we're actually hashing, whatever actually input in. So by pretending the input was a fixed string. Yes, this is basically it. That basically shows that this is legit. Like for formalizing cryptography, this is like one of the good ways that this is like legit and legal and actually means something. And it's funny because I learned it as like cryptographic engineer lore, like you just add a label to it, and that's that hash function. And it is not that different than having like 312, 350, shake. Those are domains separated by like lengths and these other constraints on them, and the size of their inputs and the size of their outputs. That's another thing that's like allowed. So now I've taken one hash function, one random oracle, and cloned it in a way that's legal, so that when you're doing all these random oracle queries and your security proofs in the random oracle model, that counts. You're not just waving at it and being like, just pretend. It's like, no, we've got some nice like theoretical crypto basis that this counts as, now I started with one random oracle and now I have 2 random oracles or 3 random oracles or 5. Yeah. When I learned that this is not just like a hack, it felt like a hack. It felt like a dirty hack. Like, no, this is like, we've got lots of theory about this. Separate using whatever domains you want, as long as other people don't know what those names are. Yeah. And this is part of why. So like, this is an example using one random oracle, SHA-512, and separating it into 5 different ones. And then for X-Wing, so inside here, this function G, this is SHA-3 512. So actually, down here, we're using SHA-3 256. We're already a little bit domain separated, but we're trying to separate from other, like, because there's only so much you can do within the scope of like what your cryptography is operating in. So like if you embed X-Wing into a higher level protocol, and it's also using the SHA-3 256 in your whole crypto scheme, there's a chance that there's some weird funniness that like you can make queries over there, and that affects like how you're able to model and separate the queries to this SHA-3 256 over here. You don't know what other people are doing with your crypto, so just domain separating it is a good idea, and it makes the proofs work nicely. Otherwise, you're just making assumptions in your proofs that don't have much basis in reality. The specific values here, because where did it go? I need to go back to the Apple stuff, because I swear, I started pointing out X-Wing, and now I've been talking about X-Wing for like 2 hours. So this is the label that's actually in the version of X-Wing that's actually being deployed. So if you look at it like this, it's a little bit of ASCII art to make it look like a X-Wing starfighter from Star Wars. That's the reference. See? Look at it. Like that? You kind of see it? Yeah. SHA-3 is a family, and they all use the same permutation to check if. Yes, they do. Yes, that is actually correct. So the SHA-3, I think there's SHA-3 224, 256, 512, and there might be another one I forget. And then there's Shake 128, Shake 256. It also uses catch-F inside, but Shake is the expandable output function version that basically like SHA-3 and all those versions of SHA-3 are like, you give me a fixed size input and I give you a fixed size output. Or sorry, you give me a variable size input and I give you a fixed size output. And Shake is I give you a variable size input and a variable size output, and you tell me how much output you want on this invocation, and I give it to you. They're very nice functions. They're very nice sponge functions, and you can use it as a KDF like we do in X-Wing, and people are trying to start to do in other places like inside of HPKE, which would be very nice. Yeah, so that's what that notation is. It's trying to be very cute about domain separation. It's supposed to be cute little ASCII art, and we'll see how it influences things. But yeah, that's why X-Wing doesn't include the ML-KEM ciphertext and the ML-KEM PK. We don't have to include it I'm pretty sure we don't have to include it for other reasons, for NCCA reasons. For DHKEM, we have to include the public keys to have it devolve to NCCA if all that stuff became junk instead of hash function. Yeah, so I am going to go all the way back up the stack. This is not useful. Okay. Well, so this is Swift Crypto. Some of the cool stuff that was like announced and walked through in their like video today is in CryptoKit. And inside CryptoKit, it's C, and they said in their video it's formally verified C, which I'm very interested in because I love formally verified crypto implementations, but I don't think we were trying to find the public version of the C in CryptoKit, and I don't think it's been uploaded yet to public places. So looking at the Swift version, there's only 2 errors: public key mismatch, initialization, and invalid seed. So we love seeds. I'm very happy to see a lot of the API decisions or KEMs that Apple is making. CryptoKit is curious what anything ML-KEM might be in it. No, I'm pretty sure Apple has very specific requirements about either they write their own code, or I don't know if they have anyone else write their own code. They would not pull in libOQS. I practically guarantee it. I don't work at Apple, but when I try to, the people I know who work at Apple are very Apple-y in that they will not tell you things that they are not allowed to tell you. I'm pretty sure there's no libOQS here. This is all Apple stuff, especially because everything in CryptoKit on iOS, and I think for anything that has a secure enclave, they're writing it to live inside the secure enclave. So when you're making queries to X-Wing and ML-KEM via CryptoKit, it's calling inside the secure enclave and doing crypto ops for you. And like, where's the thing? I think they have this is Kathy. She's awesome. She's very smart. She works on the Apple crypto team. Very cool that she gets this whole Apple video thing. I sent it to my mom. Let's see. There it is. No, is it? Oh, come on. No, not there again. Sorry. But anyway, it's all inside their secure enclave, so they're pretty persnickety about it. Yeah, I actually love this video because they actually it's a whole nother kettle of fish to ARM Trust Zone, I think. I'm a bit out of date on Apple does secure enclave, but like, it's so locked down. I know that Trust Zone has leaks and stuff. Yeah, exactly. It's like, yeah, it's pretty hardcore. Like I don't know if there's separation from their secure enclave and their like roots of trust that are burned into every Apple device that gets manufactured, but I wouldn't phrase. It's extremely important for their whole trusted compute posture. Yeah, all of this post-quantum, the HPKE ops and ML-KEM are inside the secure enclave. I wish I could like mute that from the tab. That would be very cool. Oops.
It also has secure enclave support, meaning you can enforce hardware-isolated execution for ML-KEM operations.
Support. Okay.
We discussed how you should
So maybe you can use it without the secure enclave, but you don't have to. use the secure enclave. Now, this is interesting because it almost appears like the Swift crypto stuff is actually wrapping Boring SSL. Yeah. Boring SSL is Google and Chrome's primary SSL TLS library and their main optimized crypto implementation library. There's also their developer crypto library kit called Tink. It also has cryptography implementations closer to the way that CryptoKit does. It has in multiple languages, so for like hybrid encryption, signing, things like that. But Boring SSL is TLS. It's used in Chrome. It's used on the Edge servers so that when you talk to Google and you're talking to them over TLS, Boring SSL is the thing doing the computation that's actually terminating and making your connections for you. It's in Chrome on Android and desktop. I'm pretty sure it's also just built into Android, but I'm not sure about that. And it is the source of many forks at this point. Boring was a fork of OpenSSL, and now other people have forked Boring because they want to do something that they want to tweak. And Boring only supports Google. It's not going to take PRs or suggestions. It does its own thing. And they have introduced ML-KEM and ML-DSA and a bunch of other post-quantum stuff. Yeah, they landed X-Wing just a few weeks ago, I think. They are also using it for HPKE, and I think they're using it for encrypted client hello in TLS. I think that's what I saw, but I'm not 100%. But this is interesting. But I'm going to back out of the Swift crypto just because, like, I'm not 100% and I'm looking at the CryptoKit stuff. Also, while we're talking about TLS, this was a great announcement as well today with all the post-quantum stuff that Apple's doing today. This is not CryptoKit, but for iOS, iPadOS, macOS, and visionOS, all the TLS connections are going to be preferring TLS 1.3 and hybrid post-quantum as like their preferred key establishment, which is amazing. This is already the default for Chrome, including desktop and Android. It's already supported by Cloudflare. I don't know if it's the default in Firefox, but it's definitely supported in Firefox. It's now the default for the latest version of OpenSSL. This is exciting because this means all the new, like, you'll be talking post-quantum TLS from your Apple devices by default to anyone who also speaks it, to any place on the internet that also speaks it. So, yay! Yeah. I mean, if you're using Chrome on macOS, you're already doing it, but for everything else, yeah. I am not motivated. I am very motivated with new emoji. But I just got now. I think I was applying some, updates for Xcode, the thing I never use, but I need it to be up to date because of compilers and crap during beta. Is this the new glass style, whatever they called it, that looks like underwater, under the sea? Yeah. But this is really exciting, and I think this is like similar ingredients to X-Wing, but because it's inside TLS 1.3, you don't have to do all this extra stuff with like the SHA-3 and the ciphertext and public key of X25519 and the label inside TLS 1.3, because like the TLS 1.3 key schedule is doing that already for you. It's already doing domain separation. It's already doing this key derivation for you. So all you have to do is slap in the shared secrets of those two things. Up further in the key schedule, it's taking the public key that you're sharing and the ciphertext that you're sending back. It's already including that in the key derivation schedule. So this is really nice because it's like, because of the nice design of TLS 1.3, they were able to do the simplest, tightest, most efficient way to go hybrid for hybrid post-quantum key agreement. And they didn't have to do anything else. They didn't have to make any other changes. Like there's a kilobyte of data up in the thing, but that's totally built for that. It can handle it. And everyone's been rolling it out, basically, once we figured out a couple of nitty things. Can't you use X25519 ML-KEM for similar purposes if on its own isn't quantum resistant, is it? X25519 on its own is not quantum resistant. It is a elliptic curve Diffie-Hellman key exchange. It is definitely not quantum resistant. You can use ML-KEM on its own, and it is quantum resistant. And there is a draft that is currently working its way through IETF to let you do just that. And I submitted it. It has my name on it. So full disclosure, it's very simple. You just do what you are doing for the hybrid one. You're just not doing hybrid. You're just doing the ML-KEM thing. The thing is that some of this PQ stuff is new. X25119 ML-KEM 768 is literally doing the elliptic curve Diffie-Hellman part and the ML-KEM part together. It's doing the old school way and the new school way together as a hedge. It's like a belt suspenders. Both is good. It's literally mitigate. I'll let Kathy talk because Kathy and the folks at Apple did a great job describing exactly why people are going hybrid for this scenario right now. And let's see if she gets right in there. Exactly the kind of attack sort of stuff I'm trying to address. And I really appreciate Apple
Harvesting encrypted data.
for
Harvest now.
making a video that I can just share with people that
Here's how
will
the
explain
attack
things for me. I did the work.
Going back to the previous example, the app has sensitive user data like health, location, and photos, and wants to send it to the server. It encrypts the data with TLS and sends it.
No.
An attacker observing the network can harvest that encrypted data and store it.
Oh no.
They
Anything?
can't decrypt it just yet, but they can wait until they have access to a sufficiently powerful quantum computer in the future, and then decrypt the harvested data to gain access to the sensitive user data.
Yeah, so this is yet another unfortunate collision in cryptography of the term hybrid. It's understandable to be a little bit confused because we have a scheme called HPKE, which stands for Hybrid Public Key Encryption, which is a mixture of asymmetric and symmetric. There is also hybrid post-quantum traditional or hybrid classical and quantum resistant. And this is a hybrid between asymmetric schemes of a classical security nature or a post-quantum security nature and using them together so that the thing that you finally have, something like X-Wing, is a secure scheme if one of those components fails because either the post-quantum computers arrive and the classical stuff is just hella broken and just junk. You still have like for example, X-Wing, you still have a secure KEM. Or you deploy some brand new cryptography, like these post-quantum KEMs, when you don't fully understand it yet, and there's an issue, a security issue, or it's new and there's implementation issues that we don't fully understand yet, and so there's a bug, there's just an implementation bug. And so the post-quantum part is insecure, so that you fall back to the classical security part and you're still secure, as long as the quantum computer doesn't arrive and attack your stuff. So that's why the hybrid stuff, especially for key establishment, is getting rolled out right now, because they're trying to mitigate that store now, decrypt later attack. If everyone's just watching your key establishment go over the wire when you're doing your TLS connection or your signals session setup, well, signal is post-quantum now. Same with iMessage. They're watching all that. They kind of slurp it up and store it and the ciphertext that's protected by it in a nice big data center. And then when they have the big quantum computer, they can just go through and rifle through and look for something juicy to point quantum computer at and attack it. So that's live now. So people want to move quickly now to protect their data and their traffic and all of that stuff now. Because they want to move quickly now, they're a little bit more nervous about just going directly to PQ as the line of defense of computing shared secrets and protecting their traffic against it. They want to hedge their risk by including this classical stuff that they understand very well, the elliptic curve stuff. It helps that everyone's pretty comfortable with elliptic curves at this point. Elliptic curves are very small and they're very fast, so that it's free. It's practically free computationally, mostly computationally and definitely size-wise, to just do both. If that were not the case, I don't think we would be doing hybrid, but it is the case. And so people are very, especially for key establishment, you just do elliptic curve Diffie-Hellman and you do like something like ML-KEM or another post-quantum KEM. especially in the guts of your protocol, like in TLS 1.3. But if you don't have that infrastructure of TLS 1.3 or something like it, you need to just smush a thing that's like a KEM into a random spot. You just want to wrap all that up into one nice primitive. You reach for something like X-Wing. And so that's why X-Wing is being adopted, and it's being used in HPKE, which explicitly needs a KEM. And so it was a very nice place to slot in a hybrid KEM. And there's also HPKE out there that lets you use pure ML-KEM as well, if you want to. I don't know if Apple does that, actually, so I'm gonna take a look. But yeah. And then if you want even more hybrid, there's hybrid arguments and hybrid games, like security proof games. And there's hybrid, we have HPKE, so like hybrid public key encryption, hybrid post-quantum, and there's like at least another one that I always forget. It's like in a different area that I use less often. There's far too many. The number of things called hybrid is too damn high in cryptography. Stop calling things hybrid. Okay. I'm going to go through this pretty quickly because I'm starting to fade. So okay, so we have KEMs. This enumerates all of them. Okay, so general KEMs, we have them. I think this means that I can do HPKE with CryptoKit. Hybrid Apple bridles, maybe. I could do pure ML-KEM HPKE, which is very nice. Encapsulation results. Yeah, okay. I think they're making it explicit what the components are, but I know. It is it's wild. We've been trying to get this adopted somewhere in IATF and like turn this into just draft whatever CFRG, or I don't know what they call them in ISE, X-Wing, but for reasons this has not been adopted, and so my name is on it until I don't know. Okay, so I might have talked about seeds earlier. I mentioned seeds. So when we init, this is it's not helpful. Okay, creating a private key. We're gonna look at this interesting thing in a second. This is the format that Apple has basically decided. So this is why I want the code, because this is data, but like, I'm pretty sure this is explicitly like 32 bytes of data. And I don't know, and these are slightly different, but I don't really know from these docs. And so I'm pretty sure this byte representation is a representation of the seed, which for for X-Wing is 32 bytes. And then this says the public key, but I think the integrity check representation also includes the hash of the public key. And I think what you can do is you can rederive and re-expand from the seed the full expanded encapsulation key and the full expanded public key, and then you check the hash of the public key passed in against what you computed. It's not my favorite. Like, I know it's quite computationally cheap to rederive this all the time, but cached versions of the public key exist for reasons, so I understand this, but I really want to look at the code because I think this is what the integrity check representation is inferring, but I'm not 100% sure. And yeah, the seed variant gives you the strongest binding properties that we can get from this construction, and it basically means like if anyone through data corruption or an active adversary of leaked key material getting stolen and reused and manipulated and tried to use against you, if someone tried to do that, the shared secret you compute out would vary. So it is very difficult, especially using the seed variant, for someone to try to trick you into computing like a shared secret that they're like man in the middling with and confusing someone else that they are computing their shared secret. Or, like, there's a whole bunch of like weird things you can do. It gives you really strong guarantees that the session that you're computing is independent of all the other sessions, that there's no collisions, that there's like no one can manipulate the data to like get you to decrypt something that you don't think you should be decrypting or anything like that. It's very good for security and modeling these KEM shared secrets across protocols, especially. And I'm very happy that Apple's just going for it. And then one other nice thing is that they're nice and small, and they give you like correctness and consistency guarantees across like all over the place. Like there is a one true format for all this stuff. Seed length is 64 bytes. That's correct. So that might be 32 for the actual seed. Yeah, that's ML-KEM. Yeah, that's correct. And this is always funny because ML-KEM is 64 bytes because they have the actual PKE seed, which is 32 bytes, the real seed, and they source another 32 bytes, and that's the FO rejection seed that gets combined with the attacker supplied ciphertext and computed to create a shared secret. You could, the way that X-Wing does, and the way that ML-KEM does inside its PKE actually, take a 32 byte seed and do shake 256 to it and get 64 bytes out of it. But this was already built into the draft of ML-KEM when it was being finalized by NIST, and people were just like, we would love to be able to just use the seed. And they were like, okay, you can use the seed the way it's currently written, which is these two 32 byte seeds, making a 64 byte seed total, because it's already in there and we don't have to change anything. If they wanted to do a 32 byte seed, they would have to go in, add an extra line, source 32 bits, and then that might tweak the security proofs a little bit and blah, 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 blah. So ML-KEM is 64 bytes. MLDSA is the signature scheme, and it is 32 bytes because it's constructed differently. And I'm pretty sure I saw Apple do the nice thing there as well. This is very funny. I have a feeling this is going to have reverberations throughout the industry. Apple is explicitly choosing the top security levels for both MLDSA and ML-KEM and completely skipping the category 1 security level. Oops. Yeah, you found it in Swift? Yep. Awesome. It's actually quite nice. Funny, yeah. Funny this is boring SSL wrapper, but like, okay. For Swift, I guess that kind of makes sense. But for common or CryptoKit or common crypto, I'm pretty sure that's going to be their own implementation. But yes. Yeah, seed size plus 32. Oh. Oh, wait. This is the, yeah, I'm in the wrong one. Get away from me. Cool. Yeah. Seed. Integrity rep. Drop blast 32. Yes. Ha. Look at that comment. I love a nice comment. Yep. Seed. Public key hash byte. And then they rehash. They hash bytes. Oh, they're just they're parsing it. Sorry. Oh, hi. After this X-Wing one, Swift. Oh, got it. Okay. Yep. Like that. Hold on.
Yeah. This puppy. Now 7 months old. Yeah.
20.
Yeah.
All right. Cool. What was he even talking? Okay. Seeds. We like seeds. Oh, MLDSA. That's what I was talking about. Click. You can click. You can click. There we go. Yeah. They're not using... Okay, so it wasn't category 1, but the equivalent closest in ML-KEM, they do have category 1, and that's 512. And they're dropping that completely, which is interesting. This is category 2, and they're dropping it completely as well. I'm pretty sure the industry is going to coalesce around this one because it's going to be the smallest commonly available one, and it's definitely strong enough. Like ML-KEM 768 is definitely strong enough for a number of years. It's like baking in some headroom for attacks to get better and things like that. I think that's going to be the same with MLDSA 65. I was thinking about like which scenarios might adopt MLDSA 44. I don't know if that's going to happen now. I think it just might, everyone might coalesce around 65, which is interesting because like when you have platforms like Apple, Google Cloud, AWS, Boring SSL, Open SSL, all this stuff, they set the bar and the expectations and the availability and kind of interop and things like that. I have a feeling this is going to have an effect. The signature sizes for MLDSA 65 is 3.3 kilobytes big, and the public key is almost 2 kilobytes. It's a lot of bytes. Related to that, okay, another integrity checks representation, seed representation, and public key. They're doing a similar thing here as they do in ML-KEM. And I'm gonna look at the keys. So 32 byte seed. I love a seed. Similar properties apply to the kind of the seed stuff for signatures keys. Correctness, consistency, all of that. I don't love the like seed plus hash of the public key thing because you can skew them in theory. You have to like, if there is a difference, which like between the hash of the public key and the seed, which one is correct? Because maybe you have like data corruption, you may have an adversary that's messing with your seed format, like something might be up. Which one do you believe? Do you believe the version that got generated from the seed, or do you believe the hash of the public key that someone handed to you? I'm pretty sure the answer should be the thing that's generated from the seed. This is the secret key material that you are supposedly the only one that has access to. But then what's the point of the hash public key? Like I know that there's scenarios out there where having the hash of the public key is useful for computational reasons, and it's a big public key. It's almost 2 kilobytes. If you're doing that a lot, like I can see that. So I don't know. Let's see. Here's the signing step. We don't need the public key, right? Hashing. Yeah, no. Like this H. Make the hint. Yeah. I think TR might be the... Yep, it is. So you need it for signing. That's why. It's not my favorite. But for signatures, yeah, it's not my favorite. But yeah, I think that's what we've got over here. Where's our signatures? ML-DSA. So is valid. Public key, public, private key. Signing, net, seed, and public. 32 bytes. Yes, it is. And the public key, the actual public key, and then you actually it self-document. I don't know if there's a equivalent to Emmy Schmidt paper, or actually, it might be. So this is a great post, by the way. Hi, Tiny Universe, about how because Sophie in her earlier life started out as I think an algebraic geometer. She did like, pretty sure she did her PhD in like crazy math. So like if you buy Sophie a drink at your local crypto conference, she will tell you about how all Diffie-Hellman, all possible ways to do Diffie-Hellman is actually all reduces to elliptic curve Diffie-Hellman, and how elliptic curve Diffie-Hellman is actually the ideal, like platonic ideal, but also actual everything reduces to doing elliptic curve Diffie-Hellman. And it's like, yeah, it's category theory and like group yeah, it's stuff. Anyway, this is great. Good stuff. Yeah, I don't know, format public key. Yeah, seeds. I think the Apple format is fine. It doesn't have a lot of these problems that they like allow multiple formats for your private key material proposal that was happening in the IETF, or has happened and is in OpenSSL. Was. I think it's fine. This is terrible. Like their actual private key material is the seeds, which is great. This proposal was like, you can have a seed or a fully expanded thing or both. And then it's like, well, what happens if you have any/all of those things and they have discrepancies? And it was like, big shrug. And the security people were not happy about that work. Yeah, this is a good blog. I don't think there's a paper because local dog has opinions. Indeed. I think there was a plane and she heard the plane. Okay. So we have seeds. And we have ML-DSA 65 and ML-DSA 87. We've got seeds for all of our KEMs, right? I think that's true. We've got that 1024. Yes. Yep, we've got that seed. We check representation for some reasons. This is actually interesting because this gross. Okay, I guess it doesn't. The reason I'm like curious about this is because FL transform KEMs like ML-KEM and how X-Wing inherits via ML-KEM are designed not to throw an error. Like the root they give throws an key thing. Isn't that for the keys? Not for, I think it's for the keys. Data type and Swift does not bind the link. I think the keys on parsing throw. I have to help the dog. Oh, okay, yeah. I'm less familiar with Swift, and like all of these signatures say throws for even on things like encaps and decaps, and I'm like, oh, so it's throwing because inside of it it's calling parse. Okay. Oh no, and the encapsulation is, wait a minute, that doesn't make sense. Encapsulate. Okay, either way, it's throwing on lengths. That's fine, I guess. Like it's not throwing because, like, if it threw because it was doing the internal re-encryption check and it was like, these things don't match, bro. Let's see. Boring. This is wrapping. Unsafe temporary application. Yeah, okay, yeah. I have a feeling that's all it is, and that's fine. That's just literally you, like in a Rust world, you wouldn't even be able to instantiate these types in the type system unless they were correctly formatted and whatever, and then you'd be operating that way. But this is different, and it's wrapping C and stuff like that. And I think in the boring SSL version, they do nice things anyway. It's not crap. Just because it's C doesn't mean it's crap. You lost. Where did it go? ML-KEM. Yeah, so like they're doing all these static asserts that the sizes of these things are correct of all these possible types. We're not going to look at today. Okay, I think that helped, and it shouldn't worry that much. Okay, so we've got. Oh, this is nice. This is like a full-on, like, what do you call it in wait, this is a generic struct. What do they call these things? Different. They're Enclave. Ooh. Cool. Yeah, look at that. Huh. Okay, I think this matches what they said. Generate shared secret from key HKDF. Because in the presentation they said you can do this sort of thing via the Enclave. And you can do ML-KEM via the Enclave. Yeah, look at that. But yeah, and they let you do HPKE via X-Wing via HPKE via the Enclave. But they're not exposing X-Wing just at the top level the way they are exposing ML-KEM. All right. Makes sense. Actually, am I right about that? Yeah, no, okay. They expose it in the kit. But if you want to do it in the Enclave, they let you do ML-KEMs ops in the Enclave. They let you do X-Wing ops, HPKE ops in the Enclave. Okay? I would love to ask why Apple people don't. All right, is there anything else? I'm going to go back to the little presentation thingy. Yes. Post quantum HPKE with X-Wing. ML-KEM says 1024, 65 at MLD 65 and 87. Cool. Yeah, go watch this whole video. It's really nice. So, we talked about hybrid key establishment. It's clear that they were thinking about hybrid
They
signatures.
send to a server to impersonate full key to using a sufficient.
But they don't have hybrid signatures. They do have MLDSA. They don't have a construction for any hybrid signature
use the stolen key to make a signature, which they send to the server to impersonate the user. The server accepts the attacker's signature as if it came from the user. The attacker then carries out actions on behalf of the user. The active attack I went over affects signatures. It breaks authenticity, as the attacker can forge authentication and carry out actions on behalf of the victim. It affects apps that perform user authentication, such as with WebAuth and multi-factor authentication, and apps that perform data authentication, such as with ACID signing. It is a future threat because sufficiently powerful quantum computers don't yet exist to carry out this attack. However, they are on the horizon. Quantum attacks are a very real threat to the security of widely deployed cryptography. To get ahead of these attacks, the cryptography community has been focusing on creating and secure the key cryptography, which includes the best security assurances. To tie back to the quantum attacks I discussed, the highest priority in the migration to quantum secure cryptography handles sensitive user data. Protecting against this attack is so important that Apple has already done this for iMessage. iMessage protects sensitive user conversations sent over the network. To get ahead of quantum attacks, in iOS 17.4,
The development of reliable, useful quantum computers has been continuing steadily, and there have been recent results in the past year, specifically on using surface codes to produce a very reliable logical qubit from multiple physical qubits that looks to be a bit of a tipping point. This is a very cool result that the Google quantum computing team produced. There's a lot of hype around it, but this is the good stuff. It's a whole different paradigm of computing over information. It continues to progress. The actual useful results from it are not here yet, but it's definitely one of those things of almost like a pure science endeavor of exploring this paradigm may open up possibilities that we can't even think of yet because we don't have it in front of us. And it's not just about if I have a quantum computer, then I can attack all the asymmetric cryptography that's deployed in the world. There's stuff like protein folding, chemical simulation, trying to find more efficient batteries, trying to find more efficient chemical processes, modeling large simulations such as weather or nuclear processes like fusion. Those are the kind of things that people are speculating could be applied for, but it's definitely more of a open up realms of computation and analysis that are out of reach, even for very large classical compute data centers. And then it also happens that we have cryptographic attack algorithms that are extremely efficient against RSA and all the other currently deployed asymmetric cryptography. But you would need somewhere between, the naive implementation of Shor's algorithm would need 1,000, 2,000 logical qubits, stable enough logical qubits to attack RSA 2048 or something like that. We think we are getting there, and it's not just about 2,000 physical qubits. We're probably going to do this quantum error correction using surface codes or something like it to produce logical qubits out of multiple physical qubits. There was basically a long time where it was adding more physical qubits did not actually help you reduce the error. It just compounded the error. And it's both the function of the physical engineering of the physical qubits with the algorithms. It's classical computation on the side, computing information between multiple physical to produce one stable, long-lived, reliable, logical. But they finally basically have inverted the trend. So they finally are able to get a more reliable logical qubit the more physical qubits they added to the surface code. And that's the result from the Google Quantum Willow work. That's anyone who's been keeping an eye on quantum computing, especially as a threat to classical cryptography, worried about this, because if you can just stamp out 7 by 7 physical qubits and they work and they give you a long error-free logical qubit that you can do multiple gates on and do a full-on quantum algorithm on, and it's not degrading and corroding and all that stuff, you can just stamp them out. You just replicate it, stamp them all out, and you do that 1,000 times, and you are really within spitting distance of fully cracking something like RSA 1024 or something like that. Yes, Waterloo is great. Waterloo is an excellent school. Yes, this is actually I think a lot of us were thinking that this was going to come. We just weren't really sure when this results, and then it did. And now we're aha, okay, so previously we're not really sure when to really start the clock. And now we're okay, clock's started. There's still a ton of, it's just engineering work, whatever. There's still a ton of difficult engineering work to get a intermediate scale quantum computer that lets you run quantum attack algorithms against a target that gets you a good result efficiently. There's still a ton of work to do, but all the pieces are lining up, and they're all lining up on the schedule that everyone was afraid of. And now the thing that we're worried about is we're solving the building blocks, and now it's a step function. It's a low grade slope increasing, and now it's going to jump, like, because of work like this. And like, I am not a quantum computer scientist, but stuff like this is not pie in the sky stuff. There's a lot of serious research and engineering effort and money being put into quantum computing, and it is progressing. So, but yeah, these are some pretty good things to look at. So this is great. Sim also gave a talk recently where he summarized a bunch of this stuff. And oh yes, yeah, all this quantum resistant stuff needs to be deployed now, especially to protect the stuff that you want to still remain protected from today in the next 10, 15, 20 plus years. It's like, and especially when you're in, say, the government and you're in the defense department inside your government, and you, one, have stuff that needs to be protected for 20, 30 plus years, and two, you're very bad at rotating your software and updating your software. Like when you have to have cryptography that's deployed on like a submarine and shit, like it's very hard to have like rotation cycles and update cycles of all of your protocols and your cryptography. So the stuff that you deploy now has to be secure in the next 25 plus years. Like, for example, I don't think the US government ever fully got rid of all of SHA-1. They haven't fully got, like, I'm not even sure about, like, defense or national security systems, but the rest of the federal government, like the non-defense part of the government, they still have MD5 floating around, and they still have triple Des floating around, and, like, triple Des isn't the worst in the world, but MD5 is pretty bad. Yeah, exactly. Like, because you can just hoover up this sort of stuff that, like, you can derive the stuff from the key exchange once you have a quantum computer. It's secure now because we're pretty sure no one has an efficient quantum computer that can do anything, but you could just store it. And then when you do have it, you can just go and like look at a very high value target or anything like that. And so the stuff that's happening now is vulnerable. So that's why, especially for key establishment, that's why all of this stuff is getting deployed now, because the stuff that you are doing now will be retroactively broken as soon as those computers come online. It's not trivial. That I don't know so much about. It's not trivial to move between trust profiles, period. It's not trivial to migrate between protocols of any kind, even if that's just literally use this hash function instead of that hash function. It's just hard to upgrade and migrate a very wide and diverse and slow-moving bureaucracy. Like, people are aware that there's a vulnerability active now, but they are also wary of these brand new cryptographic schemes that some people who are not cryptographers, or even people who might be cryptographers, are just not familiar with these crypto schemes or what they're based on. Or this is just a brand new stuff. They're a bit wary. They want to deploy now and they want to be secure, but they want to have like the belt and suspenders approach of like, if we swap this out completely, it's risky. But if we have the two of them going on at the same time, especially for key establishment where it's easy to do, it's definitely a lot easier than signatures. It makes you feel a little bit less scary to move now. So that's what's happening in a lot of places. Yeah, this is it. So this talk from PQ Crypto, excellent. This is a very up-to-date summary of the advances in quantum computing from an actual quantum computer scientist person. The corgis are being ridiculous.
How are they being?
They're all being very humpy little dogs. No, the David Zhao scheme was my dearly departed beloved Psych, SIDH, based on isogenes. Yeah. But yeah, I recommend this the talk. Very up to date. All right, is there anything else? Yeah, TLS. Talked about that. That's exciting. That's gonna be really nice. They're rolling it out for Apple's side, but this is already supported in a lot of servers, especially Google servers, some AWS services. Yes, custom protocols. This is funny. Yeah. Even missed coffee table. I need to figure out how to like
jump into a stream with my phone camera or something. Yeah.
Cool. Okay. Nice look.
I really want to learn more about their formally verified implementation stuff. I'm very curious because I know they deploy C, but I'm curious how they produce or verify that C.
Yeah.
Oh yeah, post-quantum HPKE.
For sure. Sensitive user data against quantum.
Yes.
How you can use
So I'm pretty sure. So the
quantum HPKE hyperspace from details about X-wing to recipient side.
I'm pretty sure. I don't know actually. Where's their? No, that's wrong. That's not where Mastodon is. Let's see. I don't know how to do this. Yeah, I know. Like, my dog is literally doing like figure eights at 100 miles an hour around the whole downstairs of our house, and the other dog is just like standing in one place and occasionally like tagging her as she goes by. Okay, I'm pretty sure I saw a post from an Apple person on the cryptography team, and they said they were verifying. Okay, so there's formal verification, especially when it comes to cryptography, is very much like you have a formal model, quote unquote, of the specification of the crypto scheme. So someone has to write a formal model. I'll give an example. So libcrux by the Crispin folks is a library that has a tool chain that they maintain because they're all a bunch of formal methods and cryptography PhDs. And they write Rust, but they also have formal models written in F star of a bunch of cryptography schemes, such as ML-KEM, ML-DSA. They might have X-Wing in here, Curve 25519, all this stuff. And then what they do is they're able to take the formal version of the cryptography scheme that kind of relies on a human, like implementing and modeling a crypto scheme written down in a standard or a paper or whatever, and being like, this is the formal model. This like is like the formalized version of the crypto scheme or the standard. And then you have the code version, which for these guys, they write a lot of Rust, but they also have done other stuff with other languages. And then their tool chain, there's a lot of annotations on the code. And what you can do is, one, you check that the code implementation is accurately and correctly verifying that is the implementation of the very formal version of the crypto spec. So that's like the number one thing. You can do other stuff like making sure that the entire implementation is panic free. So like anything you execute, no matter what parameters you give it, will never panic. And that's especially important for a bunch of C code, especially code that goes into something like your secure enclave or some other secure root of trust. You can also do things like making sure that you never compute in variable time or value dependent time in terms of like clock time or instructions to the CPU, that type of variable time based on the value of secret data. And this is actually important for ML-KEM because there was a very wide bug in a lot of implementations of Kyber, which was what ML-KEM was known for, was known as before it became a full-on standard. It was called Kyber slash. And I'll go back to the spec on the cached one, and I'll show you. So over here, we were looking at this before. You are handed, when you're handed your secret decapsulation key and a ciphertext. This ciphertext is public data. It's out in the world. Everyone can see it. It's attacker controlled. This is public data. You decrypt it using the public key encryption decryption scheme. You produce a message. You do some hashing with that message data, the kind of like nonce, the random nonce that got encrypted to you. And use some more computation. Then you compute a new ciphertext. This is you re-deriving the ciphertext. Yes, this is a side channel thing. You derive the ciphertext based on your encapsulation key that you trust because you are generating it and you're providing it, the random message that you got out the other end of this decryption based on the attacker-controlled ciphertext, and the randomness that you derived from all of the above. This ciphertext is not public data. It says ciphertext on it, but it is not the same publicly visible, untrusted data, the same as this ciphertext is. This is like, if you don't compute over this in a side channel free way, in a constant time way, you can leak information because this is being computed from attacker controlled data. So this is influenced, this value is influenced by attacker controlled data because we don't trust the ciphertext. The whole principle of in CCA KEM is that the attacker can send you whatever ciphertext it wants, and you should be, the shared secret that gets spat out the other end should be indistinguishable from any other, from random data, from any other key material, from anything else. Even under an adversary, they can give you random crap like that. So this can be random crap, including crap that may influence this recomputed ciphertext. So when you do this comparison of this recomputed ciphertext and the ciphertext that you got handed, this needs to be in constant time and leak free. And the Kyber/Vuln was using just like a divide instruction that was common on a lot of platforms, and it was not constant time. It was leaky. And so it was leaky enough to get information about this secret value because it's coming from all this crap. Yeah, go check out Kyber/. It's an interesting fix, an interesting bug that was seen in the reference implementation of Kyber, and it was seen in a lot of places. I don't remember. Let me check the Crispin blog. I don't know if they had it or if they didn't have it because they had already fixed it. They may have co-discovered it. That might have been what happened. Yeah, DJB was on Kyber/. Pardon me. Yeah. So they helped, I think, when they were in the middle of implementing their high assurance, formally verified implementation, they were checking that. So the nice thing of their kind of whole tool chain and their whole flow, it's based on the HACS tool chain, which lets you like model things in mostly Rust, but like annotations on Rust, and lets you compile down in like a with guarantees way to F*, Easy Crypt, and I think OCaml, but I forget the level of support there. And I think they also support outputting to C. So that's why I'm curious, like, did Apple work with them? Did Apple just do its own formal verification? If they did, what kind? Anyway, by default, I think everything that they annotate in F*, which is the model of ML-KEM, is secret by default. And so everything needs to be explicitly annotated as public in the model before like the whole pipeline will let you compute over things that are explicitly marked public in variable time. Otherwise, it's always like all values, unless explicitly annotated public, must be computed over in something like that. It was like everything is private unless explicitly annotated otherwise. And they just started implementing like Kyber, ML-KEM, and they discovered that they were computing over something that is private by default in variable time. And then they were like, oh, wait, even though this thing says ciphertext, is not publicly available, publicly visible, attacker-controlled ciphertext or whatever. This is not the same as the KEM ciphertext that's public. This is private and internal and is controllable, and we need to compute over it in a proper way. Is this it? Or was it literally in the compression? I'm sorry. I'm sorry. It's at a different place. That's also important, but also easy to do. Well, I don't know. Okay. Yeah, so it is that, but it's in the guts. It's not just the comparison. It's not just, is this ciphertext equal or not equal to that ciphertext? It's literally in the final computation that produces the ciphertext. Got it. Yes, this function is used in many parts of Kyber, including the decryption algorithm to produce a secret message, repeat the secret message, encapsulate a key, or divide a secret value by a constant, not guaranteed. Yeah, that is it. So it is this, not this, not line 9, but line 8. And I'll show you. Here it is. So when you are doing the actual encryption underneath, that's part of the encapsulation, you do a bunch of sampling for a bunch of vectors. You already have a matrix that's already generated as part of your key. It's like setting up common parameters, a common generator function. Oh my God, it's getting late. You do a bunch of sampling. These are your secrets and your errors. You do an NTT transform. You do your matrix transpose via your secret vector, and then you add some error, and then you go back out of NTT. So you've got this reasonable bit waiting instruction. Yes, it is. Yes, it is. There's a lot of literature and work about trying to make sure that your compiler does not optimize away your very delicately optimized and implemented constant time implementations of cryptographic algorithms, such as scalar multiplication and other things. There's a lot of literature on this, and it's really unfortunate, and it's like this cat and mouse game because compilers and computer architectures, like you compile to an instruction set, and that is the instruction set of a computer architecture. But once it gets into the actual architecture, all bets are off. Like once it gets into the computer, like hopefully the instruction that you think is constant time or whatever actually is constant time, and there's no guarantees there. So if you have cryptographic APIs or vector APIs in your computer, you kind of have to double check them. But mostly, like, you do have to nail down your compiler and all the flags that you give to your compiler and all that sort of stuff, because compilers and the computer architectures that they're trying to compile to they want to go fast. They want to take everything that they know about your program and optimize the shit out of it. They want to, like, if you have a bunch of instructions that fall out and like they're just a bunch of no ops, they'll just optimize them away. And like maybe you put in a bunch of instructions that are supposed to be no ops for, I don't know, you have some weird approach at like a verifiable delay function or something. Like you're doing something because it's like cryptographically good, but to a compiler, it's just a bunch of like shit it can get rid of. It still compiles the correct program to like input output compute correctly. And it will do that for you because computer go faster, and that's what everybody wants, right? And it uses less resources. It frees up more resources for other programs on the computer, or uses less memory, or whatever it is, or doesn't thrash the registers a different way, or whatever it is. It can be quite difficult to like nail down everything so that your compiler doesn't try to do you a favor and get rid of a bunch of stuff that you put in there explicitly because you're trying to make your implementation go constant time, side channel free, or whatever it is. Yes, exactly. This is incredible. Thomas Pernin is one of the best to ever do it on this sort of work. And even he is not exactly hopeful. Pessimist view highlights why such failures are expected to become more common. A constant time coding is or will soon become infeasible in all generality. Yep. Which is actually interesting because it makes the kind of Apple approach, which it can do because it is Apple and it controls the entire stack, tip to tail, the entire trusted compute stack and the software offerings that it gives on top of it, and the compute platform and what's living inside the compute platform. You can have a lot more guarantees by having these sort of secure element, secure enclave offerings. Like you control the CPU, you control everything that makes the CPU go, the entire instruction set architecture, the entire architecture implementation of that CPU, of the secure enclave, and you control everything that is allowed to run inside the secure enclave, and then you just offer an API to the people that call it. That is like one actual way you can get strong guarantees of the constant timeness, the side channel freeness, the trusted computeness of your cryptographic primitives or your whatever. It could just be software primitives. That's a real way to do it. So that's a different approach. But yes, so for Kyber Slash, So when you're gone into the guts of the encrypt methods, all right, so that's part of the encryption, I think, part of the ciphertext. No, not quite. And then this is the other side. So this is where you're actually taking the like shared secret random message that will like go into computing your shared secret. Like this is the secret material that you are encrypting to the other party. So this is where it's computed. So we take the transverse of that vector. Where is it? Up here? It's up here. Yeah, this is using part of the encapsulation key. And this vector that we just did over here, we computed over here. And we add an error. I think it's this polynomial element. And we add this decompressed encoded version of the message. Okay? So you use over there. This is like compress and byte encode. Oh wow, 3 hours. Actually like are part of the encryption. They're computing over like this stuff is computing over secret data. So this compress here, this, oh gosh, this is one of the annoying parts. Like I was implementing this the other day and I was like so annoyed because look at this. So you've got byte encode and byte decode, and they've got even more like down into the bitwise specifics of like how to implement these algorithms about converting bytes to bits and bits to bytes and encoding bits and bytes and stuff like that for like a big array of integers and going from an array of bytes into a bunch of d-bit integers and stuff like that. And then you have compress and decompress, and it's like you've got some elements in like Z mod Q and you're turning them from Z mod Q to d-bit elements, d-bit integers, and vice versa. And it's like it's going from a procedure, like a computational procedure, and just switching gears into math, just pure math. And these algorithms, this is where the Kyber / bug came in, because look at that. You've got 2D divided by Q, and you've got Q divided by 2D times X, which like X is the input or whatever. Yeah, X is the input, and then Y is the input. Like, it's got a division there, so why not divide? And it's a function that says compress. It doesn't say encrypt or decrypt on it, right? Like, why? Sure. It's not a total pain. It really isn't. Like, if you stick with if you are a Rust person and tries to model every type perfectly, you might take longer, like I have and I did. But if you stick to like the way it's written, it's just a lot of arrays of arrays where like one array is an array of field elements, and the field is only like mod 3300 or whatever. It's not a huge finite field the way that we do for like elliptic curves or stuff like that. It's just like you can fit the whole field element in a U64. It's nice. But you'll have like an array of U64s, and that is a polynomial element. And then you'll have a array of polynomial elements. You'll have a polynomial, so you have an array of arrays, and then that's a vector. And then occasionally you'll have matrices, which are arrays of arrays. And if you gonna go a little bit overboard, like some of us, and model all those things differently, it might take you a little bit longer. But if you don't, you can just keep it all straight in your head, and you make sure you know that array of stuff is different than that array of stuff. Like, you can just do it. For the compressed stuff, I would just go look at what boring SSL does, go look at what Crispin does and libcrux does. Those are good, safe, performant, reliable things. So actually, why don't we just do that? Where is it? Their constant time opt, compare. Here we go. There we go. So just to give you an idea, they really went to town on nailing down compressed and serialize, encode, decode, compress, decompress. Yeah, compressed and serialize is exactly what we do. Compress and byte encode. I think Rust supports ARM M4 as a target. Like, you can do it with no standard. I think you can. I'm not the type of person that I care more about writing very pretty understandable code for a generic target rather than like really going to town on like a specific ARM target. But I think Rust supports that. I think you can do it. And I don't think you need anything from standard that's not available in core that would get in your way. I think you could do it. Yeah, compress, encode. And this is Rust, but like this is all these annotations that help you do the formal verification stuff. So all these invariants, you assert that these compression factors are a certain size, things like that. Yes. I think you can do it. Yeah. I think it's definitely doable. I don't know how much of a pain it is. I do think it's doable, but this is not my domain, so maybe I'm being optimistic. Yeah. This is so funny because like look at all these invariants and annotations. Like this is all like meta stuff for the formal verification. And this is the actual line of code inside this loop that enumerates through all of the integers and or whatever. I think they're D-bit integers. But anyway, yeah, even more stuff. But yeah, I'm pretty sure that's Kyber/, because it's this shit in here that I bet you if they had made these functions, if they had written down those algorithms more like they wrote down these algorithms, that bug was less likely to occur. I have a strong feeling. But yeah, it maps the input to that. Function is used many parts of Kyber. It's meant to be secret. Direct implementation function divide a secret value by a constant. Not guaranteed. Constant time. Some compiler processor combinations may compile this division to a multiplication, but this is definitely not guaranteed. In our own code, we originally implement this function using a division, but our secret independence analysis flagged it as a potential timing leak. We looked at other implementations and I found a bunch of them. And independently, Dan Bernstein discovered the same bug a few weeks later. And then he gave it the name. Should secret independence guidelines be explicitly included in standards like FIPS 203? We certainly think so. Since otherwise any implementation directly encodes the pseudocode and standards likely be secure. Considering the number of Kyber implementations by expert developers, found this trap a serious concern. Division is not only a timing concern. Line 9, 16 is implemented as presented using an if branch. So it's a security issue. Algorithm 17, line 9. Okay. Bye, Strad. Yeah, you should go to bed. Here it is. Yes. There are two places in ML-KEM where secret values are used in division: when compressing messages and when compressing ciphertext. Let me assume the ciphertexts are public, and this is certainly what we did. But the NCPA ciphertexts are not always public in ML-KEM during decapsulation. Consequently, the ciphertext compression code must also be secret independent. When we type check the F* code compiled from our non-secret independent time ciphertext compression function, type checking fails because the division operation is not allowed on a value that is marked secret. You're rewriting all the operations, type checking goes through. Okay. Hence two links and other functions, sampling, secret random number inputs, field module as values outside this field discarded. I love that. That was another thing. These are false positives in the sense that discarded values have no further role in the algorithm and do not consider timing leak. We added the classification to allow as comparison. Without the spent classifiers, always dangerous to be carefully reviewed. Yeah. One other nice thing that the formal verification that the Crispin folks did for libcrux is that they were basically able to ensure that values never overflowed or exceeded like limbs or whatever they were doing, modular reductions and things like that. But they were doing them with signed arithmetic. They were doing them with signed values. They were doing them with like I64s instead of just U64s. And they were able to annotate their implementation so that they could like really crank hard on trying to get the most efficient implementation, the fastest implementation of field arithmetic that they could get. But they were able to go that far because they knew that they would be told if they went out of bounds or they fell out of the correctness bounds, or like it wasn't just like we had some tests, we had some unit tests and we just were like, yeah, cool, this seems to pass the test, but we don't know if the tests like what is a comprehensive test suite for modular arithmetic. Instead, it's literally like it cannot be greater than these values, and it cannot overflow, and it cannot do this, and it cannot do that. And they were able to check that they were always staying within the correct bounds, and were able to really get confidence that they were not breaking anything or writing an incorrect implementation when they were trying to do performance optimization. That's very cool stuff to me. Anyway, yep, Kyber slash, pretty cool. Very possible that bug would not have happened if not for the way that those compression functions were written. Let's see. Anything else?
End-to-end encryption. I like over ML-KEM with quantum hybrid construction. ML-KEM has a larger encryption over than
It's true.
but it is comparable or better performance than CryptoKit. Uses a formally verified implementation of ML-KEM, which has been proven to be functionally equivalent to the FIPS 203 standardized specification. It also has secure enclave support, meaning you can enforce hardware-isolated execution for ML-KEM operations. We discussed how you should encrypt data using post-quantum HPKE, which is a high-level API available in CryptoKit. Now also supports MLDSA as a signature API. Like ML-KEM, the MLDSA implementation has secure enclave support. The MLDSA API can be used to build post-quantum hybrid signatures at the application code. APIs run client-side, on device. Some protocols require cryptographic interoperability between the client and server. One of the easiest ways to support this is to use Swift Crypto on the server. Swift Crypto is a Swift library that provides API compatibility with CryptoKit for servers to ensure seamless development. This includes server compatibility for all the quantum secure APIs that CryptoKit supports in iOS 26. Note that because these quantum secure APIs are implementations of standardized protocols, you can use any standards compatible library on the server side. With these quantum secure APIs, CryptoKit and Swift Crypto, you now have the tools to protect your app from quantum attacks by migrating to quantum secure cryptography. Check out the sample code in the video resources for more examples of how to use these new APIs. Now you know how to protect your app's data against quantum attacks. First and foremost, make sure your network data is protected with quantum secure encryption in TLS. This is easy, especially if you use the recommended networking APIs, which have an infused post-quantum HPKE for encrypting data, like in the example climbing app. Quantum attacks aren't a distant possibility. They are relevant now, and we all need to get ahead of them by moving to quantum secure cryptography. So, as climbers say, send it.
Yay. Good job, Apple. This is really cool. All right. I think I'm done. Thanks, chat. Thanks for hanging out with me. Bye.